Okay, thank you for the introduction, and thanks to the organizers for inviting me to speak. My work hasn't overlapped very much with Fred's, but it just happens that this topic is maybe the closest of my work to things Fred has done. I saw that he has papers that mention several of these words in their titles, so that's a good coincidence. So I'm going to be trying to motivate the idea that we should use universes of spaces in topology more often. So I've come to use them in work in homotopy type theory, and I've found it to be a very convenient way to express things. And what I'm going to do is first just talk about the general concept of a universe and how you can use them. This is not new work, this is just sort of expository. But in some ways, it might be the main takeaway from the talk, the things that I want you to remember. Then the second topic will be based on, whoops, wrong button. Oh, there we go. The second topic will be based on the first paper listed here. It's with Ulrich Buchholz, myself, Jarl Flatten, and Egbert Reike. And there I will show how using these universes, you can give a new description of Eilenberg-Mac Lane spaces. And then the third topic is going to be based on the second paper listed here. It's got almost the same co-authors, but instead of Jarl Flatten, we have David Jas-Myers. And in that one, I'll explain how we can describe cup products and the Euler class using this point of view. Okay, so first, just a little bit of motivation. So as I said, I'm coming from the direction of homotopy type theory, but I want to make it clear I'm not going to be using the language or notation. I'm going to translate everything into traditional language, but just so you know, that's the background behind this. And one of the reasons I like working that way is I don't want to just prove things for spaces. I like to prove it also for other abstract homotopy theories, which are encoded in the idea of an infinity topos. So everything I'm going to tell you is actually true in any infinity topos, but I'm going to just phrase it for spaces just to keep it simple. Okay. One of the other reasons besides this extra generality is that certain types of constructions are much easier to deal with in this language. In particular, things where you do fiber-wise constructions, which I will be doing, things where you deal with path spaces, and things where you deal with universes, which will be the main point. So yes, I'm going to try to just convince you that this is a good idea and cover those topics mentioned in the title. Okay, so the intuitive idea of a universe is that it's supposed to be a space of spaces. Now, just as in set theory, there are size issues. So the universe will be a large space, and it should be classifying small spaces. So technically, you might choose an inaccessible cardinal to decide which things are large and which are small, but I'm not going to get into the set theoretic distinctions. But just keep in mind that the usual spaces we deal with will be called the small ones, and we're allowing ourselves some larger ones so that we have spaces big enough to be universes. So here's one way to describe the property we'd like a universe to have. So first of all, a universe isn't just a space U, it's also a map with some domain that I'm writing U hat. You might think of it as a fibration. In this talk, I'm always working in a homotopy invariant way. So if I talk about fibers, I mean homotopy fibers. If I talk about pullbacks, I mean homotopy pullbacks, and so on. So I don't need to specifically worry about maps being vibrations, and I will not be mentioning cofibrancy or fibrancy conditions explicitly. So the property we want on a map, on this map P, to call it a universe, is first of all, it should be a map whose fibers are all small, and given any other map with small fibers, there should be a pullback square of this form, and it should be unique in the space of such pullback squares. So the data of a pullback square consists of the two red maps, but there's also possibly a homotopy in there, depending on how you're working. And the collection of all that data forms a space, and I want it to be contractible. So that's the sense in which this should classify maps with small fibers. There should be a unique way to write it as a pullback up to contractible choice. So let's go with this and see what it tells us about this map. So if we take X to be a point, that means E is just some small space. And it should be classified by this map P, which tells us that at least one of the fibers of P should be equivalent to E. Okay. So that's the first thing we see when we take X to be a point. But since there should be only one choice of this red data up to a contractible space, in particular there's a connected space of such things, there should be only one component of U that contains points whose fiber is E. So if you think about that, that tells you that the components of this universe U biject with the small homotopy types, which is sort of what you'd expect for something that's supposed to be a universe of small spaces. I'm going to use this funny notation, and you'll see why in a second. I'm going to write B dot E for the component of U that classifies E when you put a point here. This point will land in some component, and I'm going to call that component B dot E, but you'll see that the notation makes sense. Okay. The next thing you can see, still taking X to be a point, is that this space of red data, it's a contractible space by assumption, and it has an action of the automorphism group of E. So this is the group of self-equivalences of E. It has an action by precomposing the top map with an equivalence of E. If you do that, you still get a pullback square. So you can act on the space of red data by E. That's a contractible space. So the homotopy quotient will be B dot E. And you can see that that homotopy quotient is in fact the component if you just do a little bit of diagram chasing. So that tells us that the loop space of B dot E has to be E, which explains why I chose that name for the component of E. Now, look at what this is telling us. It's telling us that a space of paths in this B dot E, or equivalently a space of paths in the universe, is equivalent to a space of equivalences. Okay. And you might have heard of this univalence axiom, and that's exactly what it says. It says that path spaces in the universe are equivalent to equivalences between the points in the universe. So if you hear univalence, it's really just this statement that looks quite familiar in this notation. So what we've learned from all this is that this thing that at first seems a bit mysterious, this P, all it is the disjoint union of the universe of the usual universal bundles over B dot E, where you let E range over all small homotopy types. Okay. So that's all this object really is. Now I do have to have a little bit of an aside to explain that there are some technicalities that I'm not telling you. So from the point of view of just the homotopy type of that universe, what I said is perfectly correct. If you are doing type theory where you're using a universe in a very precise way, you need to prove, or you need to construct a model for this universe that has a lot of extra properties. And that was first done by Voevodsky for simplicial sets. It was written up by Kapulkin and Lumsdaine. So that was like a foundational paper that started the whole field of homotopy type theory, knowing that we have this univalent universe with all the correct operations on it and so on. And then it was Mike Schulman who generalized this to any infinity topos, which lets us know that the things we do in homotopy type theory work more generally. Okay. You don't need to know that, but I just want to be honest that there's a lot of work that these people did to create well-behaved universes. But from the homotopy theory point of view, what I said gives a good summary. Okay, so let me give some more examples of the kinds of things you can do when you have a universe. So if I have a point in my universe, and I've written it as a capital F, it's an element of some space, so it might seem like a strange letter, but given a point there, we can look at the pre-image of that point under that universal map P, and that's some space, right? It's the homotopy fiber. I've written it P inverse, but I mean the homotopy fiber. That's a space. But I'm going to think of F as being that space. Okay. So in some sense, this is purely psychological. I'm just going to not write the P inverse or the homotopy fiber notation. When I have a point in the universe, I'm going to think of it as representing that homotopy fiber. And it's an important change in perspective that we think of the elements of U really as being spaces. So I'll give you lots of examples where I use this notation. Okay. So next I'm going to say a little bit more about another way to understand the universal property of a universe. First, I'm going to give you this way that's expressed in infinity category language, and then I'm going to write it in a way that's a bit more down to earth. So one way to say the property the universe has is that it's a representing object for a certain functor from spaces to spaces. So given a space X, I can look at I have to use infinity category language to get this to work out right. I can look at the slice category of spaces. So I'm taking all spaces with a map to X. And inside that category, where the morphisms are commuting triangles, I take just the invertible maps, so that's the core notation. And that's now an infinity groupoid, which can be thought of as a space. And this gives you a contravariant functor from spaces to spaces, and the universe represents that functor. So let me give you a more down-to-earth way to express that. This is what's a more internal form. That form requires to step outside of the category and use infinity category language, but I want to give this as an equivalence of spaces itself, or themselves. So on the right-hand side, what I've got here, this is just a space of all maps from X to U. So I've written curly brackets, but I want you to think of this as the space of all maps from between these two spaces. The left-hand side's a little bit trickier to understand. So this is going to be a space whose elements are pairs, where the first is anything in the universe, which I'm going to think of as a space like I mentioned up here. And the second element of the pair is a map from that space to X. So it's a little hard to see exactly what I mean here. What topology do you put here? How do I make a space out of this? So first, let me give you the intuition. If I have a vector bundle, we know that we could form the dual bundle, where for each fiber, I take the vector space that's in the fiber, I hom it into the reals, and I make that new vector space the new fiber of a bundle. And that's analogous to what I'm doing here. I've got the universe. It's got a bundle of spaces over it. There are various E's. And then for each one of those E's, I'm going to hom it into this fixed space X. I get a new space. And I want a new bundle that has all of those hom spaces as their spaces. Okay? And then I'm taking the total space of that. So if you want to be more precise, that's when the notations and ideas from homotopy type theory really help you. So what you're doing in a more categorical language is I'm taking this bundle, U hat over U. Then I'm also taking the trivial bundle with fiber X over U. So that's U cross X projecting to U. I've got these two bundles over U. And in that slice category, there's an internal hom that gives me a new hom bundle from the first bundle to the second. And this is the total space of that internal hom bundle. So in infinity topos language, you have these slice categories, you have internal homs in them, and that's what's really going on in that notation. Okay, so that states the universal property. It says that if I want to construct a bundle over X, it's the same as constructing a map from X to the universe. And these spaces should have the same homotopy type. All right, so I've repeated that here. And I want to just give an example to illustrate why this is useful. So if you wanted to construct a bundle over X, but X is something that has a mapping out universal property, some sort of co-limit, it's hard to do it directly from the left-hand side point of view, but the right-hand side is perfectly set up to try to map out of X. So as a simple example of that, if we take the circle, and if I wanted to define a bundle over the circle, I can define a map from the circle into the universe. And the universal property the circle has is that to define a map from it, you have to first tell me where the base point goes. So in this case, you have to choose a point F in the universe. And now you have to also give me a path from your chosen image of your base point to itself. You have to give me a loop at that point. Okay? But univalence tells me that a path in the universe from some point to itself is the same as a self-equivalence of that space. I think of that point as a space. So for example, I could choose F to be the integers. I could choose the self-equivalence to be the successor map. And if you do this, that by going across this equivalence, it constructs a bundle, and the bundle will be the universal cover of the circle. Okay. So this is a really convenient way to understand things like descent. They're sort of trivial from this point of view once you realize that you could construct bundles by mapping out of colimits. Okay, and then one last thing I want to say. So we already talked about B01. I'll just remind you, and then I'm going to introduce one of the key players in the rest of the talk. So we already talked about B0, and then I'm going to introduce B01, which is one of the key players. So remember, B0 was a component of the universe. So I've written it here. If I fix F, B0F is all the things in the universe that are equivalent to F. Remember, an equivalence between 2 points is the same as a path between them. So this is the path component of F in the universe. And in this notation, that equivalence is not part of the data. The data is just the collection of such y's. It's sort of natural that this classifies bundles with fiber y. If you're mapping into the universe but land in this component, that means you're choosing things that are equivalent to F. Okay. For example, if I did this for S0, what I get is a model for RP infinity. It's not so surprising. Okay, but now I wanted to do something slightly different. B01 of F, consists of pairs of data. The first thing is, again, an object of the universe. But the second is that I'm going to remember not an equivalence from F to Y, but a homotopy class of equivalences. So pi naught of the space of equivalences. Okay. So up above, I wasn't remembering anything about the equivalence. And here I'm just remembering a little bit, just its homotopy class. And if you're familiar with pi -1 notation, this is the case with pi -1. This is pi 0. And I could also do this for higher subscripts as well. And I get interesting things. Okay. So I'm taking this slight variant of B01. And if you remember, an equivalence is the same as a path. So I can also think of this as a homotopy class of paths from F to Y in B0F. And if you remember the construction of the universal cover of a space at some base point, you take the collection of all other points in the space along with a homotopy class of paths to the fixed base point. So this is a construction of the universal cover of B0F. So I'm going to give a name for this kind of data where I take a homotopy class of equivalences from some fixed space to some other space. I'm going to call it an F orientation of Y. Okay. And you'll see why once we get a little bit further into the talk. And so essentially by definition, this B01 of F classifies bundles whose fibers are equipped with F orientations. So now we have a notion of a sort of oriented bundle no matter what kind of F we're dealing with. Okay, so that was the end of the first bullet point in my outline. That's sort of the background about universes. Now I'm going to do a bit of a detour and talk about these spaces that we call central spaces. So for many of these slides, there's going to be a citation up in the top right that tells you the credit for all the results on that slide. So this again was Buchholz, myself, Flatten, and Reike. So this is the first of the two papers, and I'll list them again on the last slide. So we introduced this notion, which I'll explain in a moment, was actually known before, but for now let me tell it to you the way we came across it. So if we have a pointed space T, I'm going to say what it means for it to be central. So I take the space of self-equivalences of T that are in the component of the identity map. So they're homotopic to the identity map. They're not pointed self-equivalences. They're unpointed self-equivalences that happen to be homotopic to the identity. I can take such an equivalence and I can evaluate it at the base point and get a point in T. And if that map happens to be an equivalence, I say that T is central. Seems a little bit arbitrary. The name central comes from the theory of higher groups, where it actually is a way to describe the center of a higher group, and this map being an equivalence says that a higher group is equivalent to its center. So you don't need to know that, but there's some motivation behind the name. Now, OT1 of T it's a component, so it's connected, and under composition, it's an H space. So a central T is equivalent to an H space, to a connected H space, in fact. Okay. In fact, you can show it's got a unique H space structure. Here's a characterization of central spaces. I think I've said the word type a few times, but I just mean space when I say type. Here's a characterization of central spaces. So 2, 3, and 4 all involve being a connected H space. And then a condition on a pointed mapping space. So 2 says that the pointed self-maps of T are homotopically discrete, so the components are all contractible. The third one says that the pointed maps from T to its own loop space is contractible, and the fourth says the pointed maps from the suspension of T to T is contractible. Okay. It's not too hard to see that 2, 3, and 4 are equivalent. It's a little bit trickier to get the equivalence to 1. So let me give some examples. So every Eilenberg-Mac Lane space for an abelian group and positive n is central. And you can see this, you can see it with either 2 or 3, but let me explain with 3. So the loop space of an Eilenberg-Mac Lane space is an Eilenberg-Mac Lane space one dimension down. And then because you're mapping from an n-1 connected thing into an n-1 truncated thing, you can see that the mapping space is contractible. So that's one example. A non-example would be the 3-sphere. And you can use the fourth condition to see that, because there are maps from the suspension of the 3-sphere to the 3-sphere, non-trivial pointed maps. So this relates to some classical work. So while working on p-compact groups, Dwyer and Wilkerson introduced the terminology abelian, and it's exactly this condition on this evaluation map being an equivalence. So there they had extra structure on T in addition, the p-compact group structure that we don't need in our definition, but other than that, they did have that same map being an equivalence. Bousfield didn't ever name this concept, but in a proof, it appears at one point that he starts with a space with some assumptions, he shows that this evaluation map is an equivalence, and then from that, he's able to prove that such a space is a gem, a product of Eilenberg-Mac Lane spaces. Okay. So, and in fact, in a second, I'll give you a complete characterization that he gave. Now, that argument, first of all, it's a very long and complicated argument. He has one step where he just cites a 50-page paper, not any result in the paper, he just cites the whole paper. And it uses many things that we don't know how to do in homotopy type theory, so I don't know how to do it in any infinity topos, so I'm not going to rely on this result for what I want to talk about. But in terms of classical spaces, this is a known fact. Every central space is a gem. He goes on to figure out which gems are central, and it turns out that's true if and only if they have what he calls transitory homotopy groups. It means that among the homotopy groups, there are no homomorphisms from low homotopy groups to high ones, and there are no X groups from low ones to high ones, except maybe in consecutive degrees. You're allowed to have a non-trivial X in consecutive degrees because of that +2 over there. But other than that, there should be no X groups. Now, something like this won't be true in the generality I'm working. For one, in a general infinity topos, we have higher X groups as well. Even for abelian groups, you can have X2 and X3 non-trivial. So it's not going to be anything quite this simple. But under some mild additional hypotheses, I can prove this result as well for gems. And you can see some examples down at the bottom. So RP infinity cross CP infinity is central. But if I change the CP infinity to a KZ22, now the product's not central. So some products are and some aren't. It's not exactly obvious, but these conditions tell you when it happens. Okay. So I'm not going to use these results, but I am going to tell you what we do know about central spaces and how they fit into the story that I'm trying to tell you. Okay, so that's the definition. First proposition is that every central space has a d-looping. And this B01 that I defined, this is where we tie back into the universes, that turns out to be a d-looping of T when T is central. And this is pretty easy to see. So this B01, again, I named it as one thing. It's not B of something, but it turns out that it is a d-looping of OT1. So the name is appropriate. And for example, one way to see that is I defined B01 essentially to be the universal cover of B0, and we already saw that B0 is a d-looping of OT of T, and OT1 is the zero connected cover of T. So this just happens because we've de-looped that fact about the relationship between OT1 and OT. And then we know for a central space that OT1 of T is equivalent to T. So B01 is also a d-looping of T. But it's a very concrete d-looping. You can think of it as a space of T-oriented spaces. Okay, you can actually show that it has a unique d-looping. That's a slightly harder argument, but not too bad. So what I want to show next, though, is that when T is central, B01 of T is again central, which means you can iterate this process. And I want to use the second point in that proposition that gave 4 equivalent characterizations. So by that second one, I would have to show you 2 things. I'd have to show you that B01 of T is an H space. It's already connected because it's simply connected. And I have to show you that this pointed mapping space is homotopically discrete. So those will be the things that I do in the next couple of slides. Okay, so I'm doing the, yeah, I thought I had them in the other order, but I think I swapped them and then I forgot that I swapped them. So anyway, I'm doing the homotopical discreteness first. So the way we show this, and this is still joint with the same group of people, is that every pointed self-map of T has a unique d-looping. And so what I mean is if you take this mapping space, apply the loops functor to get you to loops B01 and loops B01. Those loops B01 spaces are equivalent to T, so you use those equivalences and you get a self-map of T. That map is an equivalence, is the claim, which tells you that anything in its domain has a unique up to contractible choice pre-image everything in the codomain has a unique up to contractible choice thing in the domain. Once you have that, then you get the discreteness you want because, again, by that proposition, we know that the pointed self-maps of T are homotopically discrete, and we have that equivalence. So there's a somewhat technical proof of the theorem, but once you have that, you get the discreteness that you need as part of trying to show that B01 of T is again central. Okay, we now need the H space structure. So I need to give you a binary operation on spaces that are T-oriented. Okay. So if I give you 2 spaces with a T orientation, 2 elements of B01 of T, I'm going to write paths x, y for just the space of paths between them in B01 of T. And the first proposition is that path space again has a T orientation, which seems a little bit weird, right? If I give you a couple of spaces and then look at the space of paths between them, you wouldn't expect that space to be equivalent to either of the spaces you started with. But that's what I'm saying, because x and y are equivalent to T. I'm saying that the space of paths between them also is equivalent to T. I'm going to give you a little sketch here. So I need to give you the orientation, which is a homotopy class of equivalences from T into this path space. So we have to be a little careful about choices here. I'd like to get something in pi naught of there. So if I give you a map that takes an equivalence from T between T and X, and an equivalence from T to Y, and gives me an actual equivalence here, not pi naught, then I can apply pi naught to that map, use the functoriality, and I'll get a map that only takes data where I have pi naught of this space and pi naught of this space, and I end up in pi naught of this space, which is exactly the situation I'm in. So I can assume I've got representatives for these homotopy classes. And then the path space, well, if you remember by univalence, these equivalences are paths between T and Y and T and X in the space B01. So by conjugating with those paths, I get that the path space here is equivalent to this path space at these other points. And that's just another name for the loop space. And we saw that B01 is a de-looping of T. So it falls out quite quickly once you set it up correctly. And this is going to be the thing that gives me the binary operation. There's a slight twist. I'm going to start with two things in B01 of T. I'll define this tensor notation to be the paths not from X, but from a certain dual of X. So I don't want to explain exactly what it is, but I have to kind of flip the orientation roughly on X. And that's, again, an element of B01T because I have a T orientation for it. And that turns out to make B01T into an H space, which was the other thing we needed to do. And so it follows that B01 of T is central. But then since it's central, I can take B01 of B01 of T to de-loop it, and I can keep doing that. And I find out that every central space is an infinite loop space in a unique way. So this little condition, this little centrality condition, turns out to put a lot of structure on the space. Now, of course, from Busfield's point of view, a central space is a product of Eilenberg-Mac Lane spaces, so it's not so surprising that it's an infinite loop space. But I'm getting to this result without having to go through that very difficult argument using the gems. Okay, and then the last thing, and this is the whole reason I've done this detour on central spaces is for this last corollary. So even if you forget everything else I said, this is the thing I really need. It's just a very special case. If I take B01 of a kgn, I get a de-looping of it. So I get a kgn plus 1. Okay. And that tensor on B01 is an H-space structure there. There's a unique H-space structure. So that means tensor represents addition in cohomology. So now I've given a concrete way to think of how to add cohomology classes by thinking of a cohomology class as an oriented kgn and doing this path space construction to give me a new oriented kgn. And this is the theme of what I want to say. I want to try to describe operations, things involving Eilenberg-Mac Lane spaces, using this particular de-looping to get me a hands-on feel for the elements there. Okay, so now the citation is changed. So now this is Buchholz, David Jas Myers, and Egbert Reiche, and we're into the third part of the talk and the second of the references. So we just talked about addition in cohomology, and now I want to talk about the cup product. So the cup product, if you think carefully, this space here, this is a kzn plus 1. This is a kzm plus 1. So if I took the cup product, I should end up in a kzn plus m plus 2. And I do that because I've got one de-looping out here and I've got a plus 1 over here. So this is the correct shape for how the cup product in cohomology should behave using this particular de-looping construction. Okay. So I need to try to write down a map like this. So if I give you two oriented spaces, one oriented for kzn, one oriented for kzm, here's a construction I can do. This star here is the topological join. So I'm taking my two spaces and I'm connecting them with all possible, for every pair of points, I'm putting a new line segment in. And now I'm doing the Postnikov truncation at level n plus m plus 1. So this double bar, this is maybe my one notation from type theory that I like for Postnikov truncations. So I'm taking everything up to dimension n plus m plus 1. That gives me a new space. And I want to give that an orientation. I want to give it a kn plus m plus 1, kz n plus m plus 1 orientation. So just like before, I'm supposed to give you something in pi naught of an equivalent space, and I have information in pi naught of equivalent spaces. By the functoriality of pi naught, I can get rid of the pi naughts, and so I can assume that I've got an equivalence of this type, an equivalence of this type, and now I'd like to understand the truncated join. But since x is equivalent to kzn, I can substitute that in, and y is equivalent to kzm. And then there's a little lemma here that says that when you do a truncated join like this, in this case, you're going to get a kz n plus m plus 1. What you would get in general if this was a kan and a kbm is you would get k of the tensor product, a tensor b. That's what would show up naturally in that spot. One way to see this is that the join is the suspension of the smash, and it falls out of that as well. The reason I've used join is that x and y are not pointed spaces, so that we don't have any points to take a smash product with. Okay, and then the theorem is that this operation does give you the cut product, at least up to a sign. Now the argument here is quite annoying. It's quite challenging, and we're hoping to pin down the sign, but we're down to sort of one diagram where we can't quite tell if it commutes or it commutes up to a reflection. Either way, if it turns out there's a minus sign, then we can put a dual in one spot here and make it work. So there's still one ambiguity we haven't pinned down, but other than that, we know that this gives the cut product. So this is just a way that, as far as I know, I haven't seen anyone think of the cut product as taking spaces that represent elements of Eilenberg-Mac Lane spaces and then joining them and truncating them. I think it's an interesting point of view. What time did I start? Do you remember? 12:40 roughly? So that gives me till 3:25? Yeah, okay, good. Okay, so now I'm going to talk about the last topic, Euler classes. So I'm going to be talking about sphere bundles. One reason is to prefer sphere bundles is that I can talk about them purely homotopically. I simply just take a bundle of spheres. I don't need to worry about a linear structure. So that's going to be the approach I take. Now, if I wanted to look at B01 of Sn, I'm going to be looking at pi naught of this space of equivalences from Sn to Sn. And there are two components to the space of equivalences, the orientation preserving equivalences and the orientation reversing equivalences. So a choice of an element there is exactly a choice of an orientation. That's why we've called these things T orientations in general, because when T is Sn, it exactly gives the usual notion of an orientation. And so in particular, this B01 Sn classifies oriented sphere bundles, oriented in the usual sense. And now I want to give you the Euler class, so I can do it in the universal case. I just need to give you a map from B01 Sn to the appropriate Eilenberg-Mac Lane space. And if you think about it, let's check the dimensions. Bundles with fiber Sn would come from rank n plus 1 vector bundles. And so the Euler class would be in n plus 1 dimensional cohomology, and this is a kz n plus 1. So things match up perfectly with how you should expect the Euler class to behave. And I'm going to define this map. I have to tell you what to do on an oriented n sphere. And all I'm going to do is I'm going to n truncate it. If I have an n sphere and I n truncate it, I get something of the homotopy type of a kzn. And it's easy, just like in those other cases, to show that you get a kzn orientation coming from the standard equivalence like this. So this is a map. If I have a bundle over some base represented as a map into B.1 Sn, an oriented sphere bundle, then I just compose with this and I get the map representing the Euler class in cohomology. Okay, so the theorem is that this agrees with the usual Euler class. So the moral, the intuitive way to say this is that the Euler class takes a bundle of spheres, and then it just takes each fiber and applies truncation, and now it gets a bundle of Eilenberg-Mac Lane spaces, and that's represented by a map into B.1, since these are all oriented, of KZN, which is a KZN plus 1, and that map gives you the Euler class. Again, I'd be really interested if someone knows that this point of view has ever been mentioned before. That would be really interesting. But it requires this new way of thinking about Eilenberg-Mac Lane spaces. So I think it probably hasn't been. Okay, I'm going to say something very briefly about why this agrees with the usual Euler class in a moment. If I have time, I might run out, but we'll see. But first, let me give you an example of something we can prove in a pretty concrete way. So the Euler class is supposed to be the obstruction to the existence of a section. Well, of a non-zero section, but since I've taken the sphere bundle, I could just say a section. So overall, this slide is from the second paper, but this result comes from the first paper because it's back to being a general result about central spaces. So it says if I have a central space and I have anything with a t orientation, a space Y with a t orientation, then if I look at the space of orientation preserving equivalences, so this one means I want to look at equivalences from t to y that respect the identity orientation of t and the given orientation of y, then the natural evaluation map at the base point of t down to y is an equivalence. So think about what this means. This means if you've got one of these oriented spaces and you choose a point in it, then you get an equivalence from t to y. All you had before was a homotopy class of equivalences, but this gives you a particular equivalence. This is a lot like what happens with torsors. If I have a discrete group and I have a torsor for it, so I have something where it acts freely and transitively, there's no canonical equivalence. Okay, there are many equivalences, but as soon as you pick a point in your torsor, now you get a canonical equivalence. Okay, so these t-oriented spaces should be thought of the torsors for t. And this is exactly the property that expresses that these are torsors. And it's common that, that for a discrete group, the space of torsors is a d-looping. And that's why B.1 of t is a d-looping of t, because it's the space of, it's morally the space of torsors for t. Okay, let's see how we can use that for this concrete theorem. I'd like to say that if I have an oriented sphere bundle, and if it has a section, then the Euler class is 0. Okay, so the Euler class, remember how it's defined. It's a composite of the representing map for my bundle with this map that just n truncates. So I have the classifying map for the bundle, tells me the fiber above each little b, it's whatever I get here. And the composite will send a point in b to the n truncation of the fiber over b. Having a section means that I have an element of p of b for each b. That's what my section is. But since I have a map from p of b to its truncation, I also have a point in this Eilenberg-Mac Lane space here, this KZN. But by the previous result, once I've got an element of that torsor, I get a particular equivalence between KZN and that KZN torsor, or that KZN oriented space. And by univalence, that's a path between the two within this space. And that means for each b, I've got a path from the value of this function to this base point. So those glue together to give a homotopy to the constant map. So we've reasoned by thinking of the Euler class as a family of spaces, and by using that univalence argument again. Okay, let me quickly do this. So I want to talk about the Whitney sum formula. So when you take the direct sum of two vector spaces, the unit sphere, or the unit sphere of the sum, is the join of the unit spheres. That's why joins are coming up here. So I can do this I can think of it as an operation on B ought. So I can take something that has an equivalence to Sn, something else that has an equivalence to Sm, join them. That will have the homotopy type of Sn plus m plus 1. And the orientations come along for the ride. So I have an oriented version of this join construction. And then the Whitney sum formula says that the Euler class of the join, I'm doing it in the universal case, the Euler class of the join of two oriented spheres is the cup product of the Euler classes. And the proof fits right here. So the Euler class is by definition the truncation of the thing you're taking the Euler class of. And there's a simple lemma that says that join respects connected maps. The functorial action of join respects or adds the connectivity of maps. So we have an n connected map from x to its truncation, an m connected map from y to its truncation. So the join of those will be n plus m. It's actually n plus m plus 1 truncated. And so therefore, when I apply these truncations, I get an equivalence. That's just by definition, though. On the inside, I've got the Euler class of x and the Euler class of y appearing. And then the previous result about how to compute the cup product, so there's a possible sign here, says that that's the cup product of x and y, of the Euler class of x and the Euler class of y. So in fact, the way we came up with that formula for the cup product was from trying to prove the Whitney sum formula, realizing we got to this one point where we needed that very last equivalence, and realizing that's a general fact about how cup products work. Okay, so I'm out of time, so I'm just going to flash this slide up, which just says you can also prove a Thom isomorphism, and you can show that the Euler class is the pullback of a Thom class along the zero section. That's what shows that it agrees with the usual definition of the Euler class, even though it's done in a very different way. And then this is just a summary slide. So this lists the things we've done. We've talked about oriented bundles. We've talked about addition in cohomology, multiplication in cohomology, the Euler class, the Whitney sum formula. I didn't really have time to talk about the Thom isomorphism of the Thom class, but there's a very nice way to prove the Thom isomorphism from this point of view. And there are the references. Also, many of these results have been formalized in a proof assistant, so they've been completely checked by a computer. And that's it. Thank you very much.